concepts in today's class. Okay. All right, so we got the recorder. Now we start browser. It's not available. My network is not connected. Now it is. That is kind of odd.
Something's going on.
Something is. Yep. Well, worst come to worst, I can use my cell phone and to continue to teach the class. Wait, the Moodle server is now within the district. I can't even do that anymore. It used to be under my desk, so it would be kind of independent to district resources, but now it's a part of the district resource. So if the district networking is down, there's no way I can get access to Moodle again.
Is it down?
No, I don't think so. I just got it, so it should be.
The intro to Linux class.
Huh?
Just the intro to Linux class just ended, so there's a lot of us who know how to screw things up now.
Okay. Okay, so let me turn editing on because I have to move the new homework assignment to where it's supposed to go. So there is a new homework assignment. It is right now it's right next to Treasure 2. It's called String and Compare. So we'll talk about this one after we talk about the solution of Treasure 2. So let's go ahead and try to move it. Okay, it's not letting me. There we go. And I'll put it at the beginning of topic 5 because it's kind of like a borderline between topic 4 and topic 5. We'll talk about this one later. But before we do that, we have to talk about Treasure 2 and just kind of talk about the solution and make sure that you guys understand the solution and how we can get to the solution because that part is kind of more important. So let me go to the command line and do this part. Treasure 2. All right, so here we have the beginning point, the starting point of Treasure 2, which is about the same thing as Treasure 1. The only difference is the type of instructions that we are using here, and also the end result is slightly different. So the question is, how do we approach something like this? The approach is not different from last time. It's about the same. The first thing we have to do is to understand the layout of these items here. Okay, we want to understand how these bytes are organized in terms of offset from label L1, because label L1 is the only anchor, the only bookmark that you can rely on and say, okay, I know where this is, okay? And if I know relatively where everything else is, I can still get to those things, okay? So that's why we want to kind of repeat this part here a little bit. I use a spreadsheet just because it's a convenient way to make a table. And we'll go ahead and make a new one. Spreadsheet. And take a look at the code so we can display. Okay, we can get rid of this one. All right, so now we can look at the assembly code and also the C code and also the spreadsheet side by side. And what we want to do is to figure out, okay, this is 0x2e, the first byte. The second byte is 0x67, which is the least significant byte of the dot word, which is on this line. The next one is 0x00, which is the implicit most significant byte of the dot word. And then we have the dot int, and we have to write it in little endian. So the 2e is referring to this 2e actually here, the least significant byte. And then we have the 6, 7, and then we have the 5f, and then another 2e. And then these 4 bytes, we don't know exactly what it is, okay, but we just know that the value of these 4 bytes will be L1 minus 6, because that's how we initialize this location. And also, we know that this is L1, okay, because it is the least significant byte of the dot int that is right after L1 colon, which is the definition of the label L1. So this is kind of important because you can see that the label is only referring to the memory location of 1 byte. Even though we are allocating 4 bytes at that point, L1 is really just the label or the address of 1 single byte. That has to do with the i386 being a byte addressable processor. Okay? There are other processors out there that are not exactly byte addressable. Some can address 2 bytes at a time, or they can only address 2 bytes at a time. So in this case, it is byte addressable. So L1 refers to only this location. But that location all by itself is not exactly very helpful to us because we need to refer to all 4 bytes and treat it as a 32-bit integer for it to be useful. After this, we have another 4 bytes, and together it has the value of L1 minus 7. So that's how the memory is laid out, pretty much the same way as last time, okay, because this part I did not change at all. What I changed is down here. At this point, after all of these instructions, EBX should have the value of 1731079.726 in decimal, but in hexadecimal it is 2e with 4 zeros and then 2e. Okay, that's the hexadecimal representation. All right, so what are we going to do? I mean, how do we get this done? Well, first of all, I'm going to double check and make sure that that number is in fact 2e, 4 zeros, and 2e. Yep.
When I checked the number on the calculator, it was 672E, 2E, 2E.
Yep, that's right.
Yeah.
Is
The
it?
other one was last homework.
Oh, that was it. Okay. So with this one, it's not the same. So I'll go ahead and use a calculator. Just double check. Pretty sure you're right, but I just need to know exactly what the byte pattern is. So should have that. Copy into the calculator, and in the calculator, I can turn it into programming mode, and it can display 6, 7, 2e, 2e, 2e. Okay, so you're absolutely right. Okay, so we want that pattern, 6, 7, 2e, 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 in register EBX after everything is done. So the question now is, how do we get it done? Now, there's several things that has to be very limiting, very restricted. The most significant 16-bit of EBX can only be affected by a single instruction of this entire program. So that gives you a pretty good anchoring point for that series of instructions. So I'm going to point out exactly which one we are talking about here. Okay, this one here. This is our only chance to set bit 16 to bit 31 of EBX. Because all of the other instructions, they only overwrite BX, which is the least significant 16-bit of EBX, or BL, which is the least significant 8-bit of EBX. This is the only time we can set the bits, bit 16 to bit 31, which is also known as the most significant 16 bits of EBX. Are we doing okay so far with this reason? So that means this is the only time, oops, sorry about that. This is the only time we can set 672E into the most significant part of EBX. All right, so let's write it down here. Okay. So we want 672E to be the most significant 16-bit of EBX. Okay. So now we have to look for that pattern. Now, when you look for that pattern, you are not looking for 672E. You are looking for 2E67 in bytes because of the little endian notation. So when you look at bytes in a byte by byte basis using the spreadsheet, we are now looking for 2E67, which is right here. Okay. So now that we have located this one here, what are we going to do with? How do we get those? There's one here and there's another one here. We can grab the other one. So we have 2E67 here. The question is, how do we get this 2E67 into the most significant 16 bits of EBX? If I start to copy from here, it's not going to end up the way I want it, because that in that case 2E becomes the least significant byte. This becomes the second least significant byte, and the most significant 2 bytes will be these two. I want these two to be the most significant bytes, which means this has to be the least significant byte. Is that making any sense? Is that okay? Okay, so I have this strong suspicion that I have to copy from L1 minus 1, 2, 3, 4, 5, 6 to EBX to get this done. But I'm not really quite sure that that's going to work. So instead of trying to figure out the rest of the question marks of this program, I'm going to copy this file to a second file just to make a copy of it, and then I'll just try very simple things to make sure that my understanding is correct. Is that working out okay? Okay. So instead of working with this program, I will save all the comments because that's still useful to me. But instead of working with this program right away, I'm going to copy it to, I'll just call it test 1. Okay, you can definitely come up with a more systematic way to do it. But test 1 is not going to do much. In test 1, oops. Well, test 1, yes. So in test 1, what I'm going to do is not even to worry about all the other stuff here. I will only leave myself with one single question mark here, and I say, well, I'm suspecting it is L1 minus 6 that has to go into EAX, because EAX is used as an indirect register in this instruction here. So L1 minus 6 is the location that I will be copying from into EBX. And the only thing I want to make sure is after the move L instruction, EBX ends up with a value of 672E blah 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 in hexadecimal. Yep.
So can you go over with what exactly the parentheses mean? As far as you mentioned indirect, but what does that exactly mean?
It uses the content or the value of EAX as an address. Okay. It goes to that location and copy whatever number of bytes the width of the instruction specifies.
Okay, so that grabs, so if EAX holds the address, indirecting like that gets the value at that address. So if the value is 5, it grabs 5.
Yep.
Okay.
Yep. So if you want to have a somewhat pseudo C representation of this, this is kind of saying EBX is doing something like that. That's kind of the same thing. It's not exactly the same, but it's close. Okay. All right. So we'll go ahead and test this program first. Okay. Because I just take baby steps. One little step at a time. I don't want to skip a few steps and end up with a program that does not work. Then I don't know which step failed. So we'll go ahead and try this one out. GDB test 1. List. I forgot something. Forgot to specify G-stabs. G-stabs. Link again. GDB list the program, and I need to put a breakpoint at stop here. And by the way, if you just use the beginning part of a label and press the tab key, it can auto-complete in a breakpoint command. So I just run the program. Now I'm at the breakpoint, and I say print. Well, print works. Okay, print /x. What is in EBX? And it has 672E0067. Okay, so it worked. Okay, so this part worked. So that's good. That's good confirmation. So once I know this part works, I go back to treasure 2 and go back to the location here. So right here, I basically have to say, after this instruction, EAX should be L1 minus 6. Okay, because I need EAX to be L1 minus 6 on the move L instruction. So that means the result of the add L instruction has to give me that particular result. Are we still doing okay so far? Okay. So now the question is, how do we get L1 minus 6 to be in EAX after the add L instruction? Okay. The previous instruction is another indirect operand. Okay, this one has another indirect operand. The indirect operand is, has parentheses surrounding a register. So this means I am going to memory where EAX is pointing to, grab those 4 bytes and put it back into EAX. So if you want to interpret this, in this way, then we're basically saying EAX is once again, indirect or dereferencing itself in this case. Okay. So we need a certain memory location that is kind of at least close to L1 minus 6. So we want to go into memory and say, okay, the spreadsheet actually has this listed pretty clearly. So can you see in column B anything that has to do with L1 or L1 minus 6? Anything that has L1 in it is going to be fine because we can add a constant to it. So we can always change the offset a little bit.
L1 itself has L1 minus 6.
Okay, L1 itself can be used, L1 plus 4 can be used as well, because anything that has L1 as part of the value at that location, which is this one here or this one, either one can be used. Okay, I can pick either one. L1 is referring to these 4 bytes, or the first of these 4 bytes, and that certainly can be used. Okay, so that means over here I'm going to specify L1 or L1 plus 4. It doesn't matter which one you use. You just have to make some fine tuning later on. Okay, so if I make this $L1 and not just L1 because we're dealing with an immediate operand here, then EAX will have the content or the value of L1 minus 6 after the second instruction. So I better double check that first. Okay, so I'm going to write another test program to double check this. So the key is not to write the program in one single step, or at least if I were to do this homework assignment, I would not try to do it in one single step. I'll just make little test programs like these, so that I can double check on each step and make sure that my understanding is correct. So I'm gonna copy and paste from the other program first. So we have treasure 2. We will copy these 2 instructions into this program here. All right. So this is all that I need, okay? Because I just need to know whether at stop here, EAX has a value of L1 minus 6. That's all I want to know. Okay. So now we do the same thing. Assemble gstabs -o, test2.o, test2.s, ld-o, test2, test2.o. Okay, put a breakpoint at stop here. Run the program. And now EAX should have the value of L1 minus 6. So the question is, how do we know that? How do we know EAX has a value of L1 minus 6? So the first thing we have to do is to print L1 minus 6. The problem with that is, L1 is considered to be an integer. So that is actually L1 minus 6 already. So if I print EAX in hexadecimal, that should be the same thing, and they are. The reason why this is L1, when I print L1, it is already printing L1 minus 6, is because it is not printing the value of the label itself, it is printing the value of the content at that particular address. So that's why it's a little bit tricky in this case. Are there any questions about this part? No questions? The other thing you can also do is to do a x/wx, which means I'm printing a 32-bit chunk in hexadecimal at location L1. And that shows you that at that location we have L1 minus 6. Because this is L1 itself, E minus 6 in hexadecimal is 8, and that's why we come up with this number. So are there any questions at this point? Because I think most of the questions has to do with what do we have in memory? Are we having a just some random bytes, or do we have an address at a certain memory location? So are there any questions about this at this step? No questions? Okay. So if there are no questions, then what we'll do is to continue with this program, because I have just verified the other step is also working correctly. So when I get back to treasure 1 at this point, or treasure 2, excuse me, I already know that at this time, EAX is verified to have L1 minus 6. Okay, that's the integer value in EAX, which I can also treat as an address in the indirect operand. So, that is kind of cool, because from the first experiment, I know that if EAX already has the value of L1 minus 6, we would have moved the correct 16-bit into the most significant bit 16-bit of EBX. From the second experiment, I verified that after these two instructions, EAX ends up with a value of L1 minus 6. So what do we have to add to EAX so that it does not change it? 0 would be fine. Okay. Now the alternative is to use L1 plus 4 here. Then you have to add 1, because that is L1 minus 7. So you have to add 1 to it. So there are two alternatives to get this one done. All right. Well, I have a strong suspicion this is working, but I'm not quite sure yet. So what do? I double check. So I copy these 5 lines, and I will go to test 2. Go to test 2, I'm going to change it, and then I'll save it as a different file. So we'll go ahead and paste it first, and then remove the original two lines, and then save it as test3.s. So now we have a new program called test3.s, and we'll test it. Okay, I'm going to run the program. By the time it stops, I should have 672E as the most significant 16 bits of EBX. So let's check that. And sure enough, we do. So this is how you kind of go about doing this, kind of like slowly, step by step. The homework assignment is designed to make sure that you understand the addressing modes and how memory is actually initialized using the .int construct, and also the other type of initialization constructs. So at this point, I'm done with the first 4 instructions. I just verified that. Now it's time to move on to the next set of instructions. This is the only chance for me to set a BL, to set BH, because moving into BX is overwriting the least significant 16 bits of EBX. But this is the only time that I can overwrite bit 8 to bit 15 of EBX. So that means this is the only chance to do it. The only chance to set bit, what was it again? Bit 8 to 15 of EBX. And we want it to set to 2E in hexadecimal. All right, well, we got a few 2E's around. So when we go back to the spreadsheet, we can see that we have one 2E here, and we have another 2E here, and then we have another 2E here. So we can potentially grab any one of these 3 2E's and put that into the most significant byte of BX. The least significant byte doesn't really matter, so I can copy from here to BX. I can also copy from here into BX. Either way will work. So now the question is, how do I get EAX here to become, oops, sorry about that, to become, okay, let's put some labels here. This is L1 minus 1, L1 minus 2. So we can use L1 minus 2. We can also have L1 minus 3, L1 minus 4, L1 minus is 5. So L1 minus 2 and L1 minus 5 will both work. 6 and 7. So are there any questions about why we are not copying from L1 minus 1 or L1 minus 4? No questions about that? Okay, because we want it to be in the more significant byte of a 16-bit, integer register. So we can specify L1 minus 2. Okay, so let's pick L1 minus 2. So in order for EAX here to end up with a value of L1 minus 2, there are really many ways to do it, right? I mean, you can certainly take your pick of how you want to do it. One quick and easy way is to say this is L1 minus, what was it again? 2. And just add 0 to it. That will work. You can also say this is L1 and then add -2 to it. That will work as well. The bottom line is, by the time we get to line 24, we want EAX to be L1 minus 2. That's all that we care. Are we doing okay so far with this portion? Sort of? Okay. All right, so, but we are not really sure that this is actually working, so, if I want to, I'm going to test it again, okay? Assuming this is going to work, this one is the easiest one, okay? We want to move a single byte into BL, which is the least significant byte of EBX, and we want that to be a 2E. And once again, we have our choices of which 2E we want to use. We can use L1 minus 7, L1 minus 4, or L1 minus 1. They're all 2Es. So you definitely have your pick here. Okay, you can definitely pick just L1 minus 7, okay? And that should do it too. All right. So now that we are done with Treasure 2, or we think we're done with Treasure 2, yep. Go ahead.
You might want to make that capital with that matter.
Yeah, it does. Well, let's see what happens when I make a mistake with the case, because that will help show you, what you will have to deal with when you have a typo in your program. Trash2.o, treasure2.s. Okay, so let's think about what's going to happen here. What do you think will happen? Because I have a typo error in the source code. Instead of uppercase L, I used a lowercase l. So what do you think will happen when I try to assemble the program?
It's going to try to access a label that doesn't exist.
It will have a reference to a label that is not defined within this program. But it's not going to cause a problem. The assembler will not complain, because the assembler's job is to basically just to look at the program in the source code and compile or translate the instructions into assembly code, into machine code. But if you have an undefined reference, it will just say, the linker will deal with that. Okay, because it is perfectly okay for a particular source file to have references to labels or symbols that are not defined within that file. The linker's job is to resolve all of that stuff. So the assembler is not going to complain. The assembler is happy as a clam and say, it's not a problem, okay? You have a reference to a symbol that is not defined locally. I'm assuming somebody else has a definition of that label, and the linker will be able to find it. That's what the assembler is thinking. The linker, on the other hand, is not going to be a happy camper, because I don't have any other object file specified here to define the label with a lowercase l. So it is going to complain and say, we have a problem here. Okay, we have an undefined reference to L1. But the nice thing is the linker tells you where in the source code this problem is. So it tells you this is on line 26 of the source code. So if I go back to treasure2.s on line 26, that's exactly where the problem is. Okay, because I use lowercase l instead of uppercase L here. So once I fix the problem, I have to reassemble, and then I have to relink the program. So now the program should be ready to go. So we have treasure2, put a breakpoint at stop here, run the program, do well, IR would work too, but since I've been using print/x, I'm going to keep using that one. And now we have 6, 7, 2E, 2E, 2E. So the program is now working just fine. Yep.
One of the first things I tried on that program was in the assign or in the move operator.
Mm-hmm.
I moved 0 into EAX, and then on the value of 0 in
Mhm.
EAX, or so I thought. And then in the next one, I figured I would just add 2E for that entire one, so that way I had 2E, 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 so that when I moved it into BL and BX, it would just be correct. But it would it kept giving me segmentation faults when I ran.
Because okay, let me go back to the source file and you can tell me what you did to it. And I will use line numbers here.
And I ended up doing it a different way, but I just couldn't figure out why that wouldn't work. So
Okay, what was the first way again?
what I did, let's see.
On line 16, you moved something like zeros into EAX.
I moved. This is this treasure?
This is treasure 2.
Okay. On line 22.
Okay.
Because I got past the first one. On line 22, I moved 0, the value of 0 into EAX.
Okay.
So yeah, I did that, and then on 23, I added 2E, yeah, $0.
So by the time we get here, EAX will have the value of exactly 2E in hexadecimal.
But I did 2E, because you need 4, correct?
Well, you mean like that? It
One
really
more.
does not matter because
Okay.
what you're trying to specify here is you're trying to specify something in EAX which later on is used by used in a dereference operation. And whatever you specify here, that is not a valid memory location.
Oh, that makes sense. Okay.
Because whenever you see something like this, a register in parentheses, it is indirect, which is the same thing as dereferencing a pointer.
Okay, so it was thinking that 2E was an address.
You're trying to you exactly.
Okay.
Yep.
That
So
makes
in
sense.
yep. So you're not trying to specify the content in EAX. You're trying to specify the location that has the content in EAX, and
Okay.
that's why this method would not work.
So if I were able to change that, which I wasn't, and take out the parentheses, that would have worked.
That is correct.
Okay.
Yep. But that would kind of defeat the whole purpose of the homework assignment.
Right. Thank you. That clears that up.
Yep. Yep. So that's good because that means we are actually learning something from the homework assignment. We are basically clearing up what is the operand without the parentheses. That's just a regular register operand. And with parentheses, it's called the indirect operand, which means we are dereferencing. Okay, we are treating the register as a pointer, and then we are dereferencing that pointer to copy things at the location specified by the register, but not the register itself.
Okay.
Okay, all right. Well, that is good. That's definitely helpful. So let me kind of fix the program first. I'll just not save it. All right. So that's treasure 2. So with treasure 2 out of the way, and this is really helpful. Okay, because if I did not talk about treasure 2, and talk about these concepts again, we would not be ready for string and compare. So let's move on to topic 5, which is where string and compare is. And this is your new homework assignment. It has quite a few of the same concepts that you have to deal with in the previous homework assignment, except in this case, you also have to worry about control structure. You're going to write a loop to do certain things. All right, so here is the new assignment. We'll say tar x and zvf string and compare .tar.gz and go over there. Right, so we'll take a look at the string and compare. Most of the instruction is here. So starting with this point here, use man string and compare to look up the official description of the function string and compare. But this is the pseudo C algorithm. So I'm giving you the algorithm. You don't have to come up with the algorithm. You do have to come up with the assembly code to implement the algorithm. Okay. So I just want to make sure that we understand the C code or the pseudo C code. In this case, this is a while loop. It is a pre-checking loop. This means L has to be non-zero, and whatever P1 points to has to be the same as whatever P2 points to, and P1 has to point to a non-zero thing. P1 and P2 are both character pointers. Okay, they're supposed to be character pointers. So these comparisons are supposed to be happening at a byte basis, not a 32-bit basis. Plus plus P1 or P1 plus plus, it doesn't really matter in this case. It's just incremented the pointer to point to the next one. P2 plus plus, increment the other pointer. L plus plus is to decrease the length by 1 because we have moved past 1 more byte. And then you go back here and say, okay, do we still have more characters to compare? Yes, we do. Are the characters pointed to by P1 and P2 the same? Yes, they are. And are they both non-null characters? Yes, they are. Then we have to move on again. So this is a string and compare algorithm. I'll explain it, using a spreadsheet later on. So after you get out of the loop, you have two conditional statements to evaluate. If we ran out of characters to compare in the end, then the two strings are the same because we compared every single byte that we can possibly compare, and we still cannot come up with a conclusion which one is larger and which one is smaller. So it's time to say, okay, they're the same. Or in the case of if L is not 0, and but P1 and P2 they point to the same byte, then the two strings are still the same because we still stop when P1 and P2 are pointing to the same character. So we can still come to the same conclusion. Else, if P1 is less than P2, or whatever P1 points to is less than whatever P2 points to, then the first string is considered to be less than the second string. If it is none of the above cases, then the first string is greater than the second string. Now what do we do with all these conclusions? It's down here. So insert your code here, okay? So by the time we get to the exit point of this entire algorithm, EBX should be a 1 if the strings are the same. EBX should be a 1, it should be a 0 when they are the same. Should be a 1 when string 1 is greater than string 2, and should be a negative 1 when string 1 is less than string 2. So that's what the algorithm is supposed to do, and you are going to do it in assembly in this particular program. Are we doing okay so far with what string and compare is supposed to do? Let's do it in C first. Okay, I'll write it in C completely and test it, and then you guys have a good reference point of how to do it in C, and then you can try to translate that into assembly. So we'll go ahead and use a let's see. How many people have used a string and compare before in your C class? Okay. So I'm going to write it in, I just call it main.c. And here is the pseudo algorithm. And over here, I'm going to implement it. So main, we have several things. We have an array. So we have a char array. And in this case, I'll just make P1 to be pointing to the string of ABC, and P2 to be pointing at, well, let's make it AB, and then we'll have the algorithm specified down here. We have an L, so L is just a regular integer, so we'll just say it's a regular integer. It can be 32-bit, it can be 16-bit in this case because it's not going to be a very big integer. So L is going to be 32, okay, because my string length, the maximum length is 32. And then I will specify the algorithm down here. And the first part should translate entirely just fine. So we'll just copy the code the way it is specified here. And then the second part has to do with the exit code. So I'll just do it the same way because I think for the most part it is just regular C code already. If they're the same, I will exit with a code of 0. else if P1, whatever P1 points to is less than whatever P2 points to, then I will conclude the first string is less than the second string. In that case, I exit with a code of -1. The last case is when P1 or the string pointed to by P1 is greater than the string pointed to by P2, then I will exit with a code of 1. So this is my entire program. I will have a return 0 here, which is really, really unnecessary because the conditional statement is going to exit. So the return 0 is really just completely useless. It just makes the compiler happy because main is supposed to return an int. Right, so let's go ahead and check the program and make sure that it works. So we'll go ahead and gcc-o main. See, -g here is for debugging information, so I can actually track it down line by line and figure out what it does. And it wants to, okay, standard lib, okay, the included. There we go. So what do you think main should return in this case? We'll take a look at the code. Okay, so we are comparing ABC to AB, and there's a no terminator at the end of each string. So ABC is really ABC and a no terminator, and then AB is really the same thing as AB with a no terminator. So when you compare these strings, what is happening? I'm going to use a spreadsheet, and we'll go ahead and use sheet 2 in this case. So we are comparing the first string, which is A, B, C, with a no terminator, and I'm going to use a \0 to represent a no terminator here. And then the other string is just AB, the characters AB, with a no terminator. So when we compare, according to this algorithm, okay, so let's go ahead and print for list from line 8. So according to this algorithm, we first initialize L to 32, and we'll never come to that particular limitation because both strings are much shorter than 32 bytes long. But in terms of the loop, what we're doing here is to compare L. L is 32 to begin with, which is non-zero. P1 points to the first row initially. Are they pointing to the same thing? Well, they're not pointing to the same byte, but the bytes that each one point to are the same. They have the same value. Is that making any sense? What about are they non-zero? Is P1 pointing to a non-zero byte?
Yes.
Yep. Okay. So what we do is we get into the loop. So when we get into the loop, let's see if we can list 10 to 15. Nope. List line 10. There we go. So in the loop, we increment the first pointer, so it points here. We increment the second pointer, so it points here. And then we decrement the counter L, so it becomes 31. So when we get back onto the condition of the while loop, L is 31. 31 is non-zero. We move on to look at what P1 and what P2 are pointing to. P1 is now pointing to a B. P2 is also pointing to a B, and they are the same. And since it meets the second criteria, we check the third one. Is P1 pointing to a non-null character? It's a B, it is not null. So it meets all three criteria. With a conjunction, the entire statement is true. So we move into the body of the loop. We increment P1, we increment P2, we decrement the length, so length becomes 30. And then when we get back to the first line here, when we get back to the condition, L is 30, 30 is not 0, so it's basically true. And then we move on to the second condition. Are they pointing to the same value? Not anymore. P1 is pointing to the character C, and P2 is pointing to the null character. They are not the same. With conjunction in C and C++, it is short-circuited, which means yes, as soon in the conjunction, if there's one statement that is false, if there's one component that is false, then the rest of it is not going to be evaluated. So we stop right here. We don't even bother to check whether P1 is pointing to a null character or not. So in the debugger, we now move on to the conditional statement. Yep.
Is L1 like your bounds checker, basically?
Yes.
Okay.
Yes, L1 is a bound checker because the problem is, if you are given strings without a null terminator, then the compare can kind of move on, go on forever. And string n compare is not dangerous because it's not overwriting anything. But string copy is. So a lot of times, people use string copy without the n, and they're copying basically string copy is saying, I will copy everything from the source up to the first null byte that I see. But what if the destination does not have that many bytes allocated? It doesn't care. It will just overwrite whatever is after the string itself. So if you specify string n copy, then you're putting a bound and say, okay, no matter how big the first string is, I will only copy up to this many bytes. If I run out of bytes, I'm sorry, I'm just going to stop. Okay, so string n compare is kind of the same thing, but it doesn't overwrite anything. So in a way, it's not necessary, but at the same time, it's also a safeguard against accessing memory that you're not supposed to. All right. So we are now moving on to the conditional statement. So the first one is L 0? No, it is 30, right? But by the time we exit the loop, L has a value of 30. So in this case, we have to check the second one. Okay, if L is not 0, which means we did not stop because we ran out of bytes to compare. The next question is P1 and P2 pointing to the same thing when they exit? The answer is no, they are not the same. One is pointing to a character of C, and the other one is pointing to a null character. They are not the same. Move on to line 21. Line 21 asks, is the character pointed to by P1 less than the character pointed to by P2? The ASCII code of C is definitely greater than 0, so the condition of line 21 is also false. So if that is also false, then we have no choice but to fall all the way through to line 27 and exit with a code of 1. Okay, so that's what the program is supposed to do. We'll check it. So we run, and it says, we exit with a code of 0, 1. That's confirmation that the exit code is correct in this case. Are we doing okay so far with the C version of this code? Okay. So what we'll do is we'll do 2 more experiments just to make sure that we covered the other 2 cases. So in this case, we'll go back to the source code of main, and we'll reverse these 2. Okay, so we'll make P1 point to AB, and then P2 points to ABC. And then we'll go ahead and recompile the program, and then go through GDB again. So GDB main, and this time I'll just run it to completion. It should come back and say we have an exit code of -1 or -1. It comes back with 377, which is actually -1. Okay, except it's in octal format. In octal format, each digit is a octal digit, which means it is also representing exactly 3 bits. So this becomes 1, 1 because of the 3, 1, 1, 1 because of the first 7, and then 1, 1, 1 because of the second 7, which is basically representing -1. So the exit code is actually -1 in this case. Are we still doing okay so far with this stuff here? Okay. Let's check what happens when we run out of characters to compare. Okay. So we'll go ahead and change the program, but this time we'll make it a very long string. So we'll just make it. I'm pretty sure that's more than 30 characters. That's easier. But I also want to make the last one different, okay? Because in this case, string n compare will consider both strings to be the same, because I ran out of strings to compare, or bytes to compare, because I only want to compare up to 32 bytes. And that's almost certainly is more than 32 bytes. I can double check. In VI, you can type a number, and then you specify what to do, and it will perform that operation the number of times that you specify first. So, but the problem is you cannot see it. When I type 32, you don't really see what I do on the keyboard, and then I use H, which means cursor left, That's 32 bytes. So I'm pretty sure this string is a bit more than 32 bytes. Okay? So let's go ahead, because this time it should come up with a 0. Okay? You should return a 0 this time. So we'll go ahead and recompile the program, GDB, run the program, and it exit quote unquote normally. When the program exited normally in GDB, it means it has an exit code of 0. Okay? Are we doing okay so far with the C code? So the C code is useful because you can use it as a reference and say, okay, given this string, this is the behavior that I can expect. Given this string, that is the behavior that I can expect. What about the empty string? What if I give it empty strings to begin with? In other words, what if I do something like this? An empty string is not exactly empty. An empty string has a single byte of the null character, the null terminator. So with this algorithm, you can definitely tell that L is going to be non-zero, okay, because it will still be 32. Whatever P1 points to and whatever P2 points to will be the same because they're both pointing to the null character. But the third condition is going to fail because P1, whatever P1 points to, is non-zero. Okay, so this will fail, but it is 0, but since we're looking for non-zero, so this condition will fail, so it won't enter the loop even once, and then we drop down to this case here. When we drop down to this case, L equal to 0 is false, but since this is a disjunction, we have a second chance to make the expression true. The second chance is comparing whatever P1 points to whatever P2 points to. But since both of them are pointing to a null terminator, that means it is true. And as a result, the program will exit with a code of 0. All right? So, any questions about the C code itself? Now, if there are no questions about the C code, now we want to say, okay, but how do we translate this into assembly code? And that's the whole thing. I might have to give you more than a week to work on this one, okay, because we are going to start to work on those topics today. But this is a good motivator for you guys to kind of pay attention, right? To relate what you're learning in class to the homework assignment, and work on it, as we talk about, the techniques to do this. All right. So now that we have a string n compare assignment, and I know almost for certain I have to change the due date with this one, so let me change that first. Sometimes it, sorry?
You're gonna take roll today?
Oh, good point. I keep forgetting to do that. Because I have to find the right row sheet first. So, but are there any questions about the concept that we have been talking about? No? Do you guys think that we have all the instructions that we need to get this done? We have the instructions. The trick is not with the instructions, the trick is with the techniques of how to combine the instructions. Assembly language programming, from a certain perspective, especially someone who does not know how to do it, well, because a lot of people look at assembly language in this way. It's kind of like trying to build a sand castle, okay? But you're using single grains of sand in the process. So you're using, you have super glue on one hand, and then you have, a pair of tweezers, and you're trying to make a sand castle using, grains of sand, like one at a time, to build a sand castle. It is not a uncommon, view of, assembly language programming. But the thing is, with assembly language programming, if you know how to structure a program, the first few steps are kind of like that. Okay, you have single instructions, which is kind of a big chore. But once you know the structures, then you can build bigger and bigger structures, and then even bigger ones out of the smaller ones. So before long, you have much bigger building blocks. You have like an entire building, an entire structure. You just say, okay, I want 3 of those things, like that. Okay. So we'll take a look at how to get it done, and I'm going to postpone the due date to the 28th, which is 5 more days, compared to the original due date. And then we'll move on to the notes that you will need in order to get this done. Technically speaking, to some people in this class, they can probably get started already because we have talked about the conditional branch instructions and all that stuff. But having said that, it is probably better to talk about control structures. Just a kind of more formal treatment of how to do the translation. So what we'll do is, well, first thing is to kind of talk about the purpose of this particular topic. The purpose is to have a set of rules and procedures and mechanisms so that we can step by step convert a C program into assembly code, and that's it, okay? And that's kind of what you have to do with your homework assignment, right? I gave you the C code or pseudo C code, and you have to turn it into assembly code. So given that is what you need to do and what this is about, the first thing is to talk about the control structures in C and C++. In C and C++, we have structured code like this, okay? So with this structured code, I'm using block 1 to represent an entire chunk of code, okay? Whatever you have to do for the then statement is block 1. Whatever you have to do for the else statement is block 2. So this is kind of like, they're representing placeholders, okay? C, block 1 and block 2, they're basically placeholders. So I'm gonna ask you this question. If you look at this code here, which is really nice, it is structured, it uses curly braces and all that stuff, functionally speaking, is it equivalent to this code here? Let's take a look at the second version. The second version says if C as a condition is not true, I will go to L1. And L1 is here. What is right after L1 is block 2, which is the else statement here. And after block 2, we get to the exit point. That seems to do so fine. I mean, that's okay. Okay, if C is not true, the second piece of code is going to do the right thing. What if C is true? If C is true in the original code, it will execute block 1 and then go all the way to the end. In this case, if C is true, not C is false. If not C is false, I'm not going to L1. Instead, I will perform block 1 here. That is still okay, right? I mean, because the first version of the code and the second version of the code are still doing the same thing. This is important. After you perform block 1, you have to have an unconditional branch to L2 to get out of the entire conditional statement. Okay? So at this point, have we established the equivalency of the first version of the code, which is what your cisp310 professor would expect, and the second version of the code, which uses a lot of go-tos and labels and stuff like that. Is that okay? All right. So if that is okay, we'll just go to the special case where there's no else. Some conditional statements may not have an else. If it doesn't have an else, like this one, then we are just going to check for the negation of the condition and skip around the block if the condition is false. Then if we do not skip around, that means the condition is true. We perform block 1, and here's just a label to mark the end of the entire conditional statement. Is that part okay? All right. So if this part is okay, then we are going to go to the next one, which is a pre-checking loop, which is even simpler, okay? Who would have expected a conditional statement to be kind of more nasty in a way compared to a while loop? So if this is the original code, which is a while loop, I think we all know what a while loop does, okay? It checks the condition C. If the condition C is true, we perform block 1. After we perform block 1, we go back to check condition C again. If condition C is true, we perform block 1 again. Then we go back to check condition C. So we keep doing this until condition C is false, then we get out of the loop. Okay? So we now take a look at the second block of the code and say, is it functionally the same as the first block of code? In the second block of code, I have an L1 to mark the very beginning of the entire loop. And then I have a conditional statement and say, is condition C false? Because if it is false, I'm going to go to L2. What does L2 do? It's the exit point. Okay? When we get to L2, there's nothing else to do for this particular while statement, and we move on to whatever is after the else statement. Is that behavior correct? We check for the negation of the condition C. If the negation is true, we get out of the loop. Okay? That's what you expect. So the second thing that we have to check is, what if condition C is true? If condition C is true, then not C is going to be false, which means we're not going to go to L2. If we're not going to L2, that means we are continuing execution with block 1. And is that the right behavior in the loop? If the condition C is true, we perform the block. Okay, so we perform block 1, but right after block 1, we have a unconditional branch back to L1. Is that right for a loop? Well, without that, it would not be a loop, right? Without that, it would become a if statement. So we need to go to L1 in order to get back to the beginning of the loop, check the condition again, and see whether we need to perform another iteration. So are we still doing okay so far? You know, there's a syntax error in this block of code. Go to L2 should have a semicolon at the end and not just a regular colon at the end. But in terms of the meaning of the code, it is actually still correct. Right. So next one is a post-checking loop, a do while. If you see a loop that looks like this in C, then you can translate it into something that looks like that. So with this one, we have L1 at the very beginning, just the same as the other one, but we perform block 1 first. Okay, we perform whatever is in the body of the loop, regardless, without checking any condition. After we perform block 1, then we check the condition. Is C true? Because if it is, we are going to go back to L1. That is the behavior of a do while loop in C. So are we still doing okay so far with translating structured C code into unstructured C code? Is that okay? Okay. The reason why we are doing this is because in assembly language programming, there is no structured construct in the language itself. So in order to translate C code, which is typically structured, into assembly code, we have to undo the structure part first and replace it with stuff that is easier to translate into assembly code. And that's why we have these steps. There are only 3. Yep.
So there's nothing like a for loop. We kind of have to make our own for loop.
Well, with a for loop, it is kind of like an initialization, a while loop, with a post operation at the end of the body of the while loop.
Right.
So it would still be okay and just do the while translation on the for loop. Because you can first translate a for loop into a non-for loop using the initialization before the while, the condition in the while, and then the post operation as the last thing to do in the while loop. So at that point, it becomes just a while loop, and we know how to deal with a while loop. So that's why I don't even mention a for loop. All right, so as far as control structure is concerned, these 3 are the only 3 that I would worry about. And then we have conditions like these, and how do we get rid of the negation, the disjunction, and the conjunction? That's really kind of the next question. Okay, so let's take a look at this one first. Okay, so if we start off with the code of if not C, go to L1, how do we do it without using the logical not operator? Well, the second block of code, right? The first block of code, which is basically saying go to L1 if and only if condition C is false, is really doing the same thing as this one here. This one is a very roundabout way of doing things, right? If C go to L2, and L2 is really just a continuation point, so how do we get to this go to L1? We will only get to that if and only if condition C is false. Exactly. So it would do the same thing as the original code. But in the process of making it lengthier and messier, we got rid of the negation. Okay? Now there are many ways to get rid of negation. This is one of the worst ways to get rid of negation. But some of the other ways of getting rid of negation is kind of complex, like using De Morgan's law and stuff like that. So sometimes people prefer this way and not the other ways. Next one is how do we get rid of logical OR? So if the original code says, C and D are both conditions, by the way. So if the original code says, if C or D go to L1, isn't that the same thing as, let's check C first. If C is true, go to L1 right away. because of short-circuited evaluation. Okay, if C is not true, okay, don't worry, we can check D. If D is true, then also go to L1. Would that accomplish the same thing as the original code? Yep. Okay, the code is a little bit more complex. We have 2 statements instead of 1, but in the process, we got rid of the logical OR. Next one is the last one, conjunction. If C and D, go to L1. In other words, if C is true and D is true, go to L1. Okay? Is the replacement code doing exactly the same thing? The replacement code starts with a negation of C and say, if C is not true, don't bother. Just go to L2, which is a continuation point. Is that consistent with how you interpret a conjunction with short-circuited evaluation? Okay, well, let's say C is true. If C is true, then not C is false. If not C is false, I'm not going to go to L2. So then I would evaluate the second conditional statement. So by the time I get to this statement, C is already true. Okay, otherwise I wouldn't be here. If C is true, then I say, hey, you know what? If D is also true, it's time to go to label L1. Would that accomplish the same thing as the original code? If C and D are both true, we go to L1. But in all other cases, we continue execution. Whatever is after me, just move on and execute that. It would accomplish the same thing, right? So guess what? We now have all the tools that we need to do the homework assignment. It's just a matter of working on it, step by step, slowly. Okay, the key word here is kind of slowly. All right, so this is a simple reduction. So if the original expression is, if it is not the case that x is greater than or equal to y, don't do the negation translation because it just makes things a lot messier. Just change the comparison in that case. So if there's a very easy way to do the reduction, don't do anything that is more complex. The second one is if the original expression is x is less than y or x is greater than y, it's the same thing as x is different from y. So in that case, just translate the comparison itself, and in the process, you're now getting rid of the disjunction. So the rules that we have talked about earlier are very, very mechanical, and many times there are shortcuts to make it simpler and quicker and more efficient. Are we doing okay so far with those concepts? Kind of? Okay. So when we move up and up, we have comparison. So we have basically general comparison. We talked about this already. Okay, it's just a different form of talking about it again. If you see this code, then we can translate it into assembly code using a compare and a jump conditional branch instruction. And the way you translate that is basically to relocate things a little bit, just move things around. This in C code is kind of the same thing as saying, let's compare y to x, and you have to make sure that y becomes the first operand and x becomes the second operand. So there's a little crisscrossing that you have to deal with here. But once you do the crisscrossing, the rest is pretty simple. L1, the label L1 is really the same as the label L1 here. This is a conditional branch instruction. There is no JR instruction. Okay, the R is simply stating the relational operator here. So R can be less than, greater than, less than or equal to, greater than or equal to, not equal to, equal to. But when you use less than and greater than, you have to make sure that you understand ABC is for unsigned numbers. GL, just GL are for signed numbers. So that is where you have to pay attention to the signedness of numbers, is when you perform a conditional branch. Are we still doing okay so far with this code, with this stuff here? There's an example. The example is pretty simple because we are comparing a constant of 5 with y, assuming y is in the register. So in that case, you're just comparing 5 with a $sign, making it an immediate operand, with y, which is a register, assumed to be a register in this case, and we want to go to L1. Less than or equal to is the same thing as not greater than, or in this case, if it is unsigned, it is, well, if it is unsigned, it is above. So that's why not above. So we have a not above here to L1. So it's just an example of how to do the translation. Yep.
What was your saying again about ABC?
Unsigned numbers are simple as ABC, so that's just an easy way to remember. When you look at all the conditional branch instructions, which one should I use for comparing less than? JB you can look at it as jump below, JA is jump above, and forget about JC. JC doesn't really match any result of a comparison. What about equal to? There really is a JE instruction. Okay, jump if equal to, but it really is just another name of JZ, because after you compare, after you do a subtraction, if the result is a 0, what does that tell you about the two numbers that you did subtraction on? They're the same, exactly. So JZ is the same as JE, it's just an synonym of each other. JNZ is the same thing as JNE, not equal to, means after the subtraction is a non-zero as a result. All right, so let me see if I have one complex example here. I think I do. What about nesting and labels? This one is really just practice. In practice, how do you deal with all the labels? I'll give you one example later on. And this is the example. So I'm translating this code into from C code into assembly code. Okay, and you can tell from the thumbnail this is going to be a long slide, and that's because I do the translation one step at a time. So personally, the way I do things is I would put a pound sign in front of all this regular C code, so this way I can interleave my assembly code with the original C code. So when I'm translating, I know which part I'm translating. I have a context. Okay, and whether you work your way from inside out or from outside in is entirely up to you. But what you want to do is only focus on one control structure at a time. Okay, do not try to translate everything at the same time. So in this case, I translate only one thing at a time, and we start with this one. So the initialization is done, and this is just doing that. This is before we talk about the direct operand. I'm kind of debating whether to introduce that particular addressing mode in this class. How do you access memory? What is the only operand at this point that you can use to access something in memory? The indirect operand. Okay, that's the only way you can access some content in memory. Sorry, go ahead.
You mean read from memory?
Well, you can write to too. I mean, because indirect can be the second operand, so you can overwrite something in memory with that.
Sure.
Okay, but that's the only one. Now, the nice thing of not introducing the other addressing mode, which is actually used in this case, is you don't get confused. Okay, because there are fewer things available, and the chances of getting confused is also much less. But the problem with that approach is every time you want to change something that is in memory, you have to move the address of that something into a register and then use indirect operand to do it. Okay, so you are trading simplicity of addressing mode for complexity in your program. Now, if I introduce the additional addressing modes, then your programs will be simpler. But then you also have to make sure that you can differentiate between the different types of addressing modes. So that really is the trade-off. What do you think?
More tools, the better.
The more tools, the better. So you can choose, right? If you decide that, oh, this is way too much, I would much rather make my program longer and use the fewer addressing modes, you can do that. Okay, so we'll go ahead and talk about the direct addressing mode in 5 minutes. Okay, that's all we need. That's all the time that we need to talk about that one. Okay. So the direct operand is like this. Okay, so we'll use a data section, do pretty much the same thing as we usually do, and we'll say this time we have a dot word of 0x DE12. Okay. So we're initializing those bytes to DE12, or 12 and DE because it's little endian. Okay, so if I want DE12 to be in register CX, okay, what do I do here? First, I have to move the address of the bytes in memory to a register, and then I have to use move W indirect EAX into the destination register, which is the CX, right? I mean, given only the tools that we have talked about in this class, this is the only way to make CX having the content of DE12, copying from the location L1. Is that okay? Which is, in a RISC architecture, that is exactly what you have to do in order to accomplish this. But in a cisp architecture, these two instructions can be done by a single instruction, which is move W, L1 to CX. It would accomplish exactly the same thing. In this particular context, on line 11, L1 is known as a direct operand. Now, you can now certainly see the confusion that can be caused. Because with a $sign, it is an immediate operand. Without the $sign, it is a direct operand. What is the difference? With the $sign, L1, whatever the value of the label is copied to EAX. So on line 8, I am not accessing the memory at label L1. I am saying, hey, whatever label L1 is, the value of the label itself is copied to EAX. In the case of line 11, without the $sign, it is a direct operand. With a direct operand, whatever I specify as the operand is not the content, is not the value that I'm copying. It is merely specifying the location in memory, in this case, from which I will copy the bytes. Okay? Are we doing okay with these two addressing modes? In other words, okay, let me if I write this in pseudo C code, this is basically the same thing as saying EAX is L1. That's it. Okay? EAX is whatever the expression L1 is. This one is, on the other hand, is saying CX is already doing a dereference. In this case, it will be known as a short because it's only 16-bit wide. So I'm basically interpreting L1, the label L1, as an address to a short, and then I dereference it. And that's why these two addressing modes are very different, even though in terms of syntax, they are very close. One has a $sign in front of it, the other one does not. Is that okay so far? Is anyone coming from a Java background? Because I'm pretty sure those people will be going. But you're doing okay so far? Okay, very good.
C and Java.
Oh, okay, so you know C already. Okay. But someone coming from a strictly Java background or Visual Basic would look at this code and go like, what is that? But does everybody see the difference between these two? So the second one on line 11, it is a very nice shorthand of what we used to have two instructions to do. And also the nice thing about line 11 is it does not destroy or overwrite the content of EAX. So you don't have to constantly overwrite a register to do something to memory. In this case, you can just access a location in memory. If you know where it is and it doesn't change, you can use your line 11 or direct operand to do it. And both direct and indirect operands can be the first operand or the second operand. So you can use it to read the content. You can also use it to overwrite the content of memory. Are we doing okay so far with these concepts? Is it going to help or not? I mean, since you mentioned you would like to have more tools. So now that you have this tool, do you think it's going to be helpful? Okay.
I actually was trying to do my homework, like I found that last night. I started playing around with it and it made everything confusing. So I already have gone through this. So like, you can put parentheses around that too, can't you? And then
no, you cannot.
Oh, it
putting
doesn't?
parentheses around L1 doesn't do a single thing.
Okay,
Because
I wasn't sure, because I kept trying like just different variants just to see what would pop out, so I was just looking at everything. Yeah, so I was just like playing around with it.
Okay. Yeah, but it is very important to differentiate line 8, which is an immediate operand, from line 11, which is a direct operand. They are very different. So the equivalent C code is the key. Okay, so L1 doesn't have to be a label. Okay, by the way, this can be 3, and this can be 3. But what it means is, in this case, EAX becomes just exactly 3 in this case. In this case, I am going to location 3 in memory and try to copy 2 bytes starting at location 3, which will cause a segmentation fault because location 3 is not accessible by your program. But that will further illustrate the differences between these two instructions, right? One will just copy 3 to EAX. The other one will cause a segmentation fault because it's going to location 3 and try to copy 2 bytes from location 3 and location 4 to CX in this case. Okay, so I'm just trying to make sure that you guys can differentiate between these two. Otherwise it can be an issue. All right. Yep.
But on line 9, won't we be doing the same thing as line 11?
Say again.
On line 9, won't we be doing the same thing as line 11, where you're trying to access
No.
3?
That's exactly what by the time we get to line 9, yes, it will be trying to do the same thing. Yes,
Okay.
you're absolutely right. So assuming you get through line 8 first, by the time you get to line 9, in other words, when you combine the effect of line 8 and 9 together, it is almost the same thing as exactly just line 11. The side effect is additional. In other words, line 8 and 9 will also destroy the content of EAX. In other words, whatever it was before is gone. But line 11 doesn't really affect any other registers other than CX, which is a nice feature too, because now you can keep all the other registers doing something else while you access a certain location in memory. All right. Any other questions? If there are no other questions, remember the due date is postponed by 5 days, but I would still get on it as early as possible. Okay. The way I would do it is to start with the C code, translate the C code into the flat C code without the structure, and make sure the program is still doing exactly the same thing first. Okay, so I will start with that one. Okay, Mr. Fox is outside already, and need to bail.
And he's gonna boot us.
Yep.